All right, now we're on to 2.6, systems of linear inequalities. In 2.5, we were looking at just linear inequalities individually. In 2.6, we're looking at systems of inequalities. So in these cases, we would have two or more inequalities with the same variables. So for example, we might have this one here. This y is greater than 3x plus 9, or y is less than 2x minus 1. Our solution in this case isn't, again, with our systems of linear inequalities, it's not going to be one point. Okay, just like the graphs of just one linear inequality, it was not just this line, it's all of this area. All of the shaded area is the true area. When we have systems of linear inequalities, it's one area that is our solution. Okay, one spot where y is both greater than 3x plus 9, and y is also smaller than or less than 2x minus 1. So let's look at some examples of this. If we need to graph the system of inequalities, y is less than 4, or x is greater than or equal to negative 1. Like before, we have to go through our steps. This step 1, getting them into the slope-intercept form, making them easier to graph. Step 2, actually plotting out some points to graph our lines. And remember, at this point, we need to make sure we're doing either the dashed line or the solid line based on our inequality symbol. And then lastly, we will shade. So let's look at what this is going to look like. If I use a red line for that one and a blue line for that one. Okay, this equation here, or the inequality, should I say, y is less than 4. That's going to look like the equation y equals 4. So I'll have to go up 1, 2, 3, 4, put a point right here. And it's a horizontal line right at 4. So it's all of these points would make that line. Okay, now we need to say, all right, am I going to have a dashed line or am I going to have a solid line? Well, in this case, because it's the less than 4 and it's not or equal to, I need to make it be a dashed line. So I would have all of these dashes going across here. And continuing out that way. Okay, next I need to shade in the area where y is less than that. So y can be 3, y can be 2, y can be negative 7. As long as y is less than 4, that's the area where I'm going to need to be shading at. So I'm going to use this highlighter and highlight all of the area that is less than 4. So everything below here, all of this spot is going to be less than 4. And as I highlight things, it might not touch everything, but I think we'll get the general idea. This is the area where all of these points, if I pick a point here, doesn't matter what our x value is, anything down here, the y value is going to be smaller than 4. So that's our inequality y is less than 4. Now we need to look at the inequality x is greater than or equal to negative 1. So that's going to look like the line x equals negative 1. So I go to my x line, find negative 1, and I'm going to plot some points on here. Oops, I'm doing this in black. I should be doing it in blue. These are all blue points. Okay, so this is my x equals negative 1 points. Because it is the greater than or equal to, I have to do a solid line here. Continues off. Mine gets a little bit curved there, but you can see it's going to be a solid line there. And I need to shade everywhere that is greater than that, or everywhere that is above negative 1. So x could be 3, x could be 0. As long as x is bigger than negative 1, it works. So that's going to be all of this area and above. Now watch what happens when I intersect this area that was with our y is less than 4. Notice how all of the spot where both of them are true, where y is less than 4 and x is bigger than negative 1, that becomes a green area. Okay, so all of the blue area, that's where just x is bigger than negative 1. All of the yellow area is true just for y is less than 4. All of this green area, though, that's saying that both of our conditions are true. Both y is smaller than 0 and x is bigger than or equal to negative 1. So your solution in this case would be all of this area. Everything in here would be what you shade in. Okay, so we're not concerned with this, we're not concerned with this, we are concerned with this area. Okay, and it's really important that you draw this line off on the side as solid and this one is dashed. But then say everything shaded in here, this is our solution. This is the spot where these two are true. Let's look at another example. I have the two lines, or the two inequalities, y is less than negative 6 plus 3, and y is less than negative x plus 2. Okay, so I'll use red and blue. For our red line here, first step is to get them into a slope-intercept form, and it's already there. Okay, y equals mx plus b. So I can use my b, 3, and go 1, 2, 3. That's my y-intercept. Negative 6 says go down 1, 2, 3, 4, 5, 6, and over 1 to the right one, because we're reading from left to right. Oops, don't need all that. Now from here to here is going to be my line, but let me get a nice red colored line. It's going to continue on like that. But I need to make sure that I'm doing a dashed line because it's not equal to. It's just the dashed line going through that area. Okay. Also, I need to make sure that I'm shading in the right area. Y is less than that, so y is all of this area over here. Now, I'm not going to go through and shade everything. I'm just going to draw some arrows so I'm reminded, or I remember, that's the area that is true for all of this. Let's look at our blue one now. Y is less than negative x plus 2. Well, again, it's already in a mx plus b form. I've got this plus 2, so I just go up 1, 2. This is going to be my point. I have negative x, which is like a negative 1x, so I'm going down 1 to the right one, down 1 to the right one. Both of these have a negative slope, so looking left to right, they're both going downwards. This one's going to go in the opposite direction this way as well. Again, because it's the just less than, not the or equal to, I need to make sure that I don't have a solid line, that I have a dashed line, like so. And again, I need to make sure that I'm graphing in the, or shading, should I say, in the right direction, less than that, so I need to go everywhere down here. So let's look at the area then, the only spot where all three of them, or both lines, should I say, are true. This area, nothing is shaded, so we don't need to worry about that. This area, kind of in this triangle, only the blue one would be shaded. So we don't use that one because we want both of them. This one, only the red area, or the red line, would be shaded. We don't want the area that has both of them shaded. So it's going to be all of this. All of this area is less than the blue line and less than the red line. So we would do something like this. Again, my shading is going to look kind of incomplete using the computer, but it's all of this area and beyond. So even all this stuff out here is also included. All of this is the spot where y is less than negative 6x plus 3 and y is less than negative x plus 2. So this would be your solution. Again, make sure this line on the edge, the boundary line, is dashed. Make sure this boundary line is dashed, because we're saying we're not including those parts, but everywhere beneath both of those parts, everywhere in here, that's a true spot for our system of inequalities. All right, let's look at this system of inequalities. We've got x plus 3y is less than 6, and 2x plus y is greater than or equal to negative 3. Well, the first thing we need to do is get them into a y equals mx plus b form, and neither of them are there. So we have some work to do with each of them. In our first one, we would start with x plus 3y is less than 6, and we could subtract x from both sides. If you subtract x on both sides, you'd be left with positive 3y, or just 3y, is less than negative x plus 6, or this is a positive 6, so we're still going up 6 from there. Now we're not done yet because we still have 3 times y, and we want y alone, so we'd have to divide both sides by 3 to get y is less than. We think of this as being a negative 1x. Well, negative 1 divided by 3, because we divided to get this 3 out of there, would become a negative 1/3 x. 6 divided by 3 would just become 2. So our new inequality would be y is less than negative 1/3 x plus 2. So if we're to draw a line for that one, we'd go up to 2. We're going down 1 and over 1, 2, 3. Down 1 over 1, 2, 3. We can go the other direction. We can go left 1, 2, 3, and up 1. 1, 2, 3, and up 1. Notice how all these points should line up. So if I were to connect them, start here, come all the way over. Remember, there's a dashed line because it's just less than, not or equal to. So it's a red dashed line going across there. And it's less than that area, so it's all of this spot. Everywhere below that line is where we'd be shading. Okay, let's look at our other one. We had 2x plus y is greater than or equal to negative 3. We need to get y alone, so we subtract 2x from both sides. That would leave us with y is greater than or equal to negative 2x minus 3. This negative 3 is still right here, minus 3, or it's like saying adding on negative 3. 2x was subtracted from both sides, so we got rid of it here, and it became like a negative 2x here, or subtracting 2x, going down 2x. So now our inequality is y is greater than or equal to negative 2x minus 3. And we need to graph that one. If we're at negative 3, or that's our y-intercept, down 3, we go 1, 2, 3 down from the origin. And our slope says negative 2, which is like negative 2 over 1. So down 2 over 1. And if we went another down 2 over 1, we'd be off chart, but it would be somewhere there. Going the opposite direction, it would be like saying going up 2 and left 1. Up 2, left 1. From there, then, this one is going to be a solid line because we have the or equal to. So we need to make sure we have a solid line. We'll do a blue one. Start here, go all the way through. There's our line. Again, this one being solid. And we're greater than or equal to that, so we need to make sure that we're shading everywhere above this line, so everywhere in this direction. Okay. This big area up here, we're not going to use. It's only the blue that would be shaded over here. This little area, well, neither of them are shaded, so we're not going to use that one. This area, only the red one is shaded, so we wouldn't use that one. We want this area. Both the blue and the red are true in this spot. So on mine, the way I'm shading it might look like a Christmas tree. So all of this area is what's true. Again, this border on the top is a dotted line. This bottom border is a solid line, but all of this area inside is true. If I picked any of those points, plugged them in, that point would be true for both of these two inequalities. Any point in here you can plug in and it would be a true inequality. So this is our solution to this system of inequalities. All right, let's look at an example of a problem we might come up against using these systems of inequalities. Example 4 says, in order to be elected President of the United States, candidates must be at least 35 years old and win a minimum of 270 votes from the Electoral College. Okay, so if we need at least 35 years old and win a minimum of 270 votes from the Electoral College, that means you can be 35, you can be 36, you can be 37, you can be 38, you can be 104, but you can't be anything less than that. So 34, 33, 21, 18, none of those would work. So we would want, first off, let's define our variables, x being our age, y being how many electoral votes you get. So the first part of our inequality would be that x, your age, needs to be greater than or equal to 35. You can be exactly 35, so equal to, or anything bigger than 35. That's the only way that you are eligible to be the president. So that's one of our inequalities. The other one, if y is our electoral votes, we need a minimum of 270. So we can get exactly 270. We can get 271. We can get 275. We can get 312. We can't get 200 or 269 or 154. We can't get anything less than that. So y, our number of electoral votes, needs to be greater than or equal to 270. That's going to be our system of inequalities, these two right here. Going on to B then, we need to graph our system of inequalities. Okay, we are going to use this graph, but we're going to scale it kind of differently. We're actually going to say, as we go along our x-axis here, how many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's use 5s. So each of these is 5. So here we'll start at 0 and 0. Here is 5. So 5 years old, 10 years old, 15, 20, 25, 30, 35 years old right here. Now according to our inequality, you can be exactly 35 years old. So all of the people, oops, I should just go straight up, solid line because we have the or equal to. All of the people right here and above, this is the area and above, so we'd be shading to the right, where you can be at as far as age to say that yes, you are eligible to be the president. If anybody is less than that, so if our age is somewhere over here, again at 5, at 15, at 20, at 18, somewhere in here, anywhere within here, you are not eligible to be president. So your age has to be somewhere over here. Going up on our scale here, I'm actually going to move these off to the side. Oops, there we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We might need to go by 30s then. We'll call this, oops, I want to use black. This is 30 electoral votes, 60, 90, 120, 150, 180, 210, 240, 270, right here. So at 270 is where you are actually able, as long as you get this many votes, so this side is votes, this side is age. In fact, we might write that down. Age is on the x-axis. V-O-T-E-S. It's on our y-axis. As long as you have 270 or more. So solid line across, continuing on, and everywhere above. that area is where, yes, you are eligible to be president. Now, let's say you got somewhere over here, you got at least 270 votes. We'll say this next one up here would be 300. So let's say you got right here, you got 300 electoral votes, but you're only 5, 10, 15, 20 years old right here. Because this isn't shaded in both areas, this would not be possible or not be okay for you. If you're 20 years old and you got 300 electoral votes, you still could not be president. You're not eligible because you're not 35 or older. The only area where it would still be okay is everywhere in here. This is all of the spots where you're both old enough and you're getting enough votes. This is the area where, yes, if somebody lands in here, they can/will be president. So name one possible solution. Let's go right here. This spot is within our eligible area. So it looks like their age would be 5, 10, 15, 20, 25, 30, 35, 40, 45 right here. And we said this was at 300. So one possible solution is 45 years old and 300 electoral votes. .45 and 300. Actually, we can even write that in as 45, 300. What that's saying is age is X, 45 years old. Electoral votes is Y, 300 of them. So this person would be eligible. Let's look at our last question then. Is 52 to 35 a solution? Well, 52, looking over here, this was 45, this would be 50. About right here is 52. And 235, 30, 60, 90, 120, 150, 180, 210, 240. So 235 would be somewhere around here. This person lands right about here. Would this be a solution? Is this person eligible to be president? Well, no. Even though the candidate is old enough, 52 years old, they're definitely old enough to be president. 235, they did not receive enough electoral votes. And again, we can look at our graph and see this point right here. That's definitely not in the zone where we're able to get be president. We're not eligible. So yes, they're in this area. They're above the age, but they're not above the right amount for electoral votes. And that would be graphing systems of linear inequalities.